Hello, we're going to talk about three-dimensional force systems, and I think this discussion is good to have it in a recording. Uh, it's only a one-person discussion with me, but this way it allows you to stop the video and really understand what I say as I go through the procedures. Three-dimensional force systems are just like two-dimensional force systems. Um, in the way that you solve them. In the 2D, you have some of the forces in X, some of the forces in Y. Now you have some of the forces in Z. And this is very important because the same procedure follows. You draw a 3D free body diagram. Remember, it's important that you always draw a free body diagram and work your problem from the free body diagram, not from the original diagram. That leads to errors. So we're going to basically talk about those equations of equilibrium and explain with an example. Life is 3D, so it's important to understand 3D systems. Many times we simplify procedures in 2D, but it's not always possible. In this case, for example, we have a weight, and this weight of this electromagnet is connected to this crane by these chains, and you need to know those forces in the chains so that you select a chain that can withstand that force, right? And so that's why this class is related to statics and mechanics of materials as well, because you have to choose the materials. This case is similar. You have a weight here, so you need to make sure that you choose these structural elements that support the force of the weight that you're going to have for this. That's why when you buy like fishing poles, they tell you how many pounds it can stand, because more than that can break it. And this, and also the support system, so it has a lot of importance. Of course, this cable as well. It's just the same as this. So this is a very important concept. So as I mentioned, the equations of 3D are just like in 2D. Remember, it's in bold, so this is a vector. So for equilibrium conditions, some of the forces in X equals 0, some of the forces in Y equals 0, and some of the forces in Z equals 0. So whenever we have the equilibrium equations for particles or for a point, in 2D, you can have two unknowns. In 3D, you can have three unknowns, okay? Because then you have three equations, and in order to have statistically determined structure, you have to have the same number of unknowns as equations. So let's do this with an example. We have four forces here, and one of the forces is this weight, and then you have three cables. So we have three unknowns, and we have to find the tension in each cable. Of course, the first step, always the free body diagram. We'll write the unknown cable forces in Cartesian vector form, so we know which ones are the elements or the the projections in X and Y and Z, so that then we can have the three equilibrium conditions or equations for solving the tension. Okay, so what I'm going to do is go with the easy ones first. Here's the diagram, and then of course here is my free body diagram. So I'm going to start with the easy one. So let's say that this is the weight, right? So the vector for the weight, this goes in the direction of negative z, so it's negative 300k. So this is my vector for the weight. That's easy. TB is another one that's easy. So TB, the vector for TB is going to be equal to the magnitude of TB, and then it's on X only, so it's I. So I have my vector for TB. Now, for TD, I have three angles. So let's see what those angles are. Because if you have three angles, you start saying, okay, it's alpha, beta, and gamma. But remember, alpha, beta, and gamma are the angles with respect to the positive axis, not the negative axis. So when I look at this angle here, maybe I can use a different color. Let me see. So I look at this angle here, and this angle is from the vector to the positive x. So in fact, this angle here is alpha. So I have alpha, oops, sorry, so alpha equals 120. So alpha is with respect to x. Then I look at another color. Let me put here purple. So this 45 degree is from the vector to the positive z. So that angle, in fact, is gamma, is 45. Now let's take a look at beta. This angle here, this angle here is to the negative y, not the positive y. So that means that I don't have beta there. Instead, beta is going to be 180 minus 60, so it's going to be 120 as well. So in the case of this 3D, if you have alpha, beta, and gamma, in those cases you don't have to worry so much about the direction of the vector in terms of its positive or negative, because the angle itself will give you that negative and positive notation. Okay, so let me see that. Let me explain that. So we have here TB. Okay, so my vector TB is going to be equal to TB cosine of 120I plus TB cosine of 120J plus TB cosine of 45K. Okay. So when I solve this for my TB, what I have is TB, hang on, not TB, I'm sorry, it's TD. D here, not TB. T, D, T, D, T, D, T, D. Okay, apologize for that. So TD, now I was looking at this here. So TD negative 0.5I minus 0.5J plus 0.7071K. Okay, and then remember, one thing I forgot is that these are all pounds. So summarizing here, my vector would be TD 5I minus TD 0.5J plus TD 0.7071K pounds. Okay, so let me highlight. This is TD, this is TB, and this is the force. So now I have to work on TD, and I want to do that separate. So let's do TD by itself. Okay. So TC. Let's take a look at TC. So the first thing you need to notice is that the angles that it's giving me, it's not, none of them are alpha nor beta nor gamma. I have an angle here to the projection here, is 30, and this is the projection TC prime, which is the projection of vector TC on the XY plane. So that's not the projector, it's the projection of the vector. Okay, so that's the first thing. Then let's take a look at what are the components in X, Y, and Z. When I look at this part here, this here is the projection, or the component in this case, in X. Okay, so, and this is negative. Okay, it goes in the negative X. Then I look at this here, and this is the component of the vector in Y, and that is positive. And then I look, let me erase this. I'll put it this way. And then this distance here, this is TC in Z. Okay, so we're going to look at this part first. Okay, so I know that TCX is going to be equal if I have my triangle. So this here is my right angle, and then this, of course, is my right angle. So you need to visualize this in 3D so that you can apply your functions, trigonometry functions. So TCX is going to be equal to TC prime, which is the projection, right, times this sine. Okay, this is here, this is the angle of 30, the sine of 30 degrees. Now what is TC prime? TC prime, then it's related to TC in this other triangle here that I have here. So TC would be equal to the vector TC, the magnitude, and then in this case it would be the cosine of 60. Okay, so combining these two expressions, TCX is going to be equal to TC cosine of 60 times sine of 30. And then we follow the same procedure for TCY. So TCY in this case is TC prime, but then it would not be the sine, it would be here the cosine, the adjacent cosine of 30 degrees, and of course we know TC prime, it's TC cosine of 60. So we combine these two, and TCY equals TC cosine of 60 times cosine of 30 degrees. So then TZZ, when I look at that, it's TC times then the opposite, so it would be sine of 60 degrees. Now, let's take a look at the positive. So the x is negative, so we need to make sure we have, this is positive, so this is negative. So this would be in x, in y, and in z. Okay, so what I want to do is to then do a summary of all the expressions, okay, and I like to express it in, let's do TB, the vector TB, the vector TC, the vector TD, and then of course the weight. So TB is going to be equal to TBI, then TC, and if we go back to TC here, okay, we can solve for these expressions already. So here we have TCX is going to be equal to negative 0.25I, and then TCY is going to be equal to 0.4433J, and then of course here we have 0.866K for TCZ. Okay. Whenever we have that already, so we have what. So what we're going to do is just write it in our summary here. Okay. So we have TC then would be negative 0.25 TCI plus 0.433 TCJ plus 0.866 TCK. And then TD, we have minus 0.5 TDI plus negative 0.5 TDJ plus 0.7071 TDK, and then of course the weight, which is Z, is negative 3K. So I like to put it in this way because then this here is each one of your equations. So this will be equal to 0, 0, and 0. So those are the three equations. Okay, so we have right here, sum of the forces in X equals 0 for equilibrium. So what we have is TB, everything that it's related to X, 0.25 TC minus 0.5 TD equals 0. This is the first equation. The second equation, sum of the forces in Y equals 0. So we have 0.433 TC minus 0.5 TD equals 0, and sum of the forces in Z equals 0, so we have 0.866 TC plus 0.7071 TD minus 300 equal 0. So you cannot get away from this problem. You have three equations with three unknowns, and There's different ways that you can do this, and I might post some help in solving equations, but here I have C and D, so I can express 1, so this would be equation 1, 2, and 3, so I can express TC as TD and then substitute in equation 3 and then obtain 1, then the other, and then I go back to equation 1. So it's important that if you don't understand or know how to solve a system of 3 equations with 3 unknowns, that you review that, okay? And so when we solve this expression, TC equals 203 pounds, TD equals 176 pounds, and TB equals 139 pounds. I hope that this helps and that you had an opportunity to pause as you didn't understand something I said. So thank you for your attention. Here's the summary before I apply the equilibriums, which is exactly